Welcome everyone to our third GDS tutorial. Please note that this tutorial is being recorded and the recording will be posted on the APS YouTube channel. We encourage you at any point to raise your hand and ask questions, but if you are not comfortable with your voice or video being posted on the YouTube channel, please use the chat. We'll be monitoring both the chat and raised hands throughout the seminar, so feel free to let us know if you have a question at any time. I would like to welcome you by giving you a chance to provide anonymous feedback to us with the QR code you see on the screen on your left. During or after the seminar, if you find that we did something well and you would like to let us know we did something well so it continues to happen, or if you'd like to let us know that something needs to change, please submit that feedback to the Google form there and we'll make sure that we make these experiences the best we can. The middle QR code will take you to a GitHub, which contains the material for every tutorial in the series. They are arranged by date, so the third folder named with today's date is the one we're going to use today, but you can also look through any of the materials for any of the other tutorials as well. If you are not already a member of GDS, but you have found these tutorials useful, I would encourage you to join GDS at the QR code on the right. If you have suggestions for future tutorials, any topics that you want to see covered, or any speakers you would like to have, feel free to email me at the email you see on the screen, and we'll make sure that we get those scheduled at some point in the future. For our next tutorial, we'll have Dr. Trevor Rohn, who will be giving us a talk on unsupervised machine learning. This will be on May 9th at 1 p.m. Eastern, so this is the standard time for the tutorials. If you attended the APS Global Physics Summit, Dr. Rohn will be given the same talk he gave at the short course that we hosted there as well. If you're interested in the material from prior tutorials, you can find links to the recordings and materials on the Engage website. And you can also go directly to the YouTube website with either of these QR codes. And I'll just give you a quick look on the Engage website for GDS. On the tutorial series button, we have a table here, which gives you not only the upcoming talks, links to register for them, but also open sessions as well. So if you want to give a talk, or if you have a topic you'd like to suggest, you can also suggest a specific date. But here you can view the recordings for the prior two sessions. And after this session is done and the recording is over, this button here that says register will convert to view recording. So you can go back through the material. And I will stop sharing now and turn it over for our speaker.
All right, good morning, everyone. I'm Ivo Dinov here at the University of Michigan. Please allow me to share my screen very quickly. Thank you, Julie, for getting us organized, and the entire data science group at the American Physical Society. The group is very active, as many of you know, with close to 2,500 or 3,000 members. It is a great community. Now, I will post in the chat the direct link just in case some of the folks that arrived a few minutes later might not have seen. So, Julie, perhaps in a minute or two, you can share it again with some of the folks that might have joined late. So, this, as Julie said, this is not really a seminar, but more of a hands-on exploration of various ideas. Hopefully, many of us get something out of it that's worth our time. So thank you for being here. I'll try to make this hopefully interesting. But I will tell you two things. First of all, I'm a firm believer of open science. So everything that the Statistics Online Computational Resource, or SOCR, develops is either openly accessible and fully accessible on the line, or it doesn't exist. So in that aspect, I am not going to run anything outside of the browser, just to as they say, eat my own dog food, do as I preach, and hopefully some of the resources might be interested for some of your research. So Now, in presentation mode, I'm not going to be, I don't have a direct access to the posts in the comments. So Julie, if I miss for a minute or two a raised hand or a comment, please stop me in my tracks. I will try to monitor, but just in case. So this should be more of a discussion.
This is going to be the first in a series of.
Okay, yeah. So as people join, it might be a good idea just to mute themselves. And by all means, unmute yourself when you have to jump in here. I would not be offended if you take the podium and ask questions or express an opinion or share something else that might be relevant. So with that, I hope everybody can see my screen. Just a thumbs up, or one or two people if you can kind of just confirm that audio, video, and screen sharing are working fine before we dive in.
Yep.
Okay, sounds good. Thank you. All right, so in case, again, the links were posted, the QR codes, but just in case you can't, you don't know where to start, SOCR, Statistics Online Computational Resource, News, Google search soccer news, you get to the wiki page, and under today's date, obviously, is where we're going to start. So the website of the American Physical Society Group on Data Science is linked to right up here. So that's where you should actually start, and then when you order by year, you can actually get to the resource as well. So all the materials are here: data sets, a complete end-to-end workflow, and so forth. So welcome again. So my presentation today is on complex time. Okay, is on complex time representation, statistical inference, and AI predictions for processes that involve repeated measurement of some spatial temporal data. So I'm not going to read all the abstract, but generally speaking, you see, we are going to go over some of these topics. I hope this is large enough resolution for people to see. So we're going to talk about, first of all, what is really complex time from a mathematical physics perspective. Then we're going to talk about how do we import repeated measurement data. How do we transform these from, let's call them time series or time courses, into something that we call kime surfaces. So these kime surfaces are going to be parametric representations. They're two-dimensional manifolds that are parameterized by time, and then the repeated sampling index, which we're going to be referring to as the phase. Okay, and then we're going to talk a little bit about forward predictions using that representation, comparisons between cohorts and groups, and then obviously things like unsupervised clustering, as well as supervised prediction modeling and so forth, that's based on the original observations on the original time courses transformed as kime surfaces. And then we are going to also see this notion of the low-dimensional representation of the repeated measurements data, and then statistical, topological, and all kinds of other things. So, well, the first thing that I want to start with is justifying a brief moment, just in a minute or two, the reason for using R and R Markdown electronic notebooks to do this demonstration. Now, obviously, the same processes can be done in any language. It could be done in pure C, it could be done in Java, it could be done in TypeScript, Python, and so forth. But I want to just take a brief moment here. Yeah, again, for the folks that join a little bit, a little bit later, perhaps if you can mute unless you intentionally want to jump in, that will be most useful. Thank you. So any questions here before we kind of dive into the details? Is everybody with me? Does everybody know how to find the resources? If not, perhaps Julie can post the link in the website quickly. But here is a rationale again of why using R. right? So there is advantages and disadvantages to every language, okay? So I'm not gonna go deeply over these, but this would be an important comparison, okay? So this kind of table talks about the importance of open science, the importance of speed, especially in the current modern times of AI-driven inference. Compute time and speed are synonymous a little bit. And then the richness of the library extent of different packages and different environments is listed here, the costs associated with diving into, and the interoperability. For me personally, the interoperability is something pivotal, right? Whether or not you can always come in and out of a platform is critical for open science. So, all right, so, and you know, there is a few graphs here that kind of show you why R is important. So with that, now, if you don't have R, don't worry about it. You can always install and run these things later, but there are a few basic things that you will need to be able to reproduce what I'm about to show, okay? So the first thing is that you have to have the base R installed, and here are the link to how to do this. I tend to use an integrated development environment that's built on top of base R. You know, for Python, this could be Spider, this could be, you know, Google Copilot, it could be a variety of things. So because we're using R, the POSIT is one of these non-for-profit but private organizations that's for the public good, I guess, that distributes the RStudio. So you're going to need this. And if there is interest at some point, I can actually open my RStudio and show you really hands-on how you run these workflows. You need appropriate packages installed and so forth. And again, I'm not going to go through all of these links because they're somewhat, you know, kind of basic. Everybody knows how to do this. And the package that we have developed to support complex time representation is called Time Complexity and Inferential Uncertainty, TCIU. So that's the direct link to the basic things that you need if you're interested in, for example, using the space kime analytics that I'm about to describe, using them for modeling some of your processes, okay? Okay, just looking at the chat real quick. Now, there is also some test data sets that in case you don't have data sets, you're welcome to use some of our three-dimensional and four-dimensional brain imaging data sets. So these are spatial temporal signals of brain structure or anatomy or physiology and function. So the fMRI is functional, the PET is physiological states of the brain. So these are data sets that we have direct links to if you want to read. If you want to reproduce these things. And then, you know, downloading any of these data sets, if you want to know, well, what are these things really looking like, you can always go to the brain viewer. And the brain viewer, you can drag and drop, literally drag and drop your nifty compressed data sets into it. And you can see them in 3D, you can browse through, you know, you can kind of manipulate your data and you know, do whatever is necessary to explore some of these high dimensional data that's kind of complex, okay? So again, if you're interested in using any of these or other three-dimensional structures, we've done this, for example, with modeling the COVID, SARS-CoV-2 virus and so forth. So if you have a three-dimensional, if you have the need for three-dimensional viewing, the brain viewer is one of these things. Now, most of the background information is contained in our data science time complexity and inferential uncertainty space kime analytics textbook. So if you want to have really the deep quantum physics underpinnings of complex time representation, that's where you probably want to start. And now the bulk of what we are about to do will have to do with these two things. Okay, so that's where we are going to be diving in now into the technical aspects of what is complex time and how do we use it to analyze real data. So I want to pause again for a very brief 10 seconds here just to see if anybody's not oriented as to where to find stuff, what are some of the preliminaries that you might need before I actually dive into the more technical presentation. All right, seeing no comments, we'll press on then. So that's going to be our main part of the tutorial here. So by the way, if you're not very familiar with R Markdown, electronic notebooks, and so forth, I would recommend you do a little bit of background research. The power of an electronic Markdown notebook is that you can, in the same single human-readable file, describe the end-to-end scientific protocol from the study design through the mathematical modeling to the computational algorithmic implementation to the data import, ingestion, and analytics to the results, reporting, and publishing. Literally, you do everything in this markdown format. It's just mesmerizing how this thing works, okay? So what's behind this, what it seems to be, as you can see here, an HTML rendition of a website. What's behind this is this R Markdown source. So you can actually see, this is the source, right? So Markdown syntax, it has a title, subtitle, theme, prints the date, and these are direct correspondences to what you actually see rendered on the page when you compile or knit this Markdown electronic notebook, which basically means you run it through its entirety through somewhat of a compiler. In R, it's actually called a knitter that actually can export it in Word, it export it in HTML, it can export it in PDF, any format that you want the report or the electronic Markdown notebook to be either human or machine readable. So again, we're not going to spend a whole bunch of time. We're not going to spend a whole bunch of time over here, right? Because even though this is human readable, right, it's somewhat cryptic, right? It's got a lot of Markdown syntax. Here is where a chunk of our code starts. Here is a link, you know, this is, okay, and all that, right? So it's got various things that are somewhat pleasant, but some things that are not particularly pleasant. So we're not going to spend time here, but that's what's under the hood, and it's very important to understand why and how these electronic Markdown notebooks work. And please forgive me, I don't mean to be, probably most of you already know that, but because there is a fair amount of heterogeneity of the audience, I thought it was probably worth it spending a little bit of time on that background. So from now on, so we're going to be going now over this. You can see that there's a table of content here that kind of allows us to quickly navigate to a specific section and all that. So we're going to start at the beginning, kind of right at the beginning here. So again, reiteration of the goals. I'm not going to restate them. Some of the dependencies, right? So here is examples of the packages that might be necessary here to run these things, the electronic notebook. And then again, now notice how for ease of human interpretation of that tutorial, all the code is kind of folded. But if you want, you can actually see it all, and then the notebook becomes a little bit more, you know, human-machine blended, which we're going to do this on demand. For now, I'm going to hide all the code, okay, just so that we can, as humans, quickly march through the content and see how things are working in practice. So, but again, if you hit a segment where you don't know exactly what's going on, you can kind of enable and see what's behind the code, right? So in the beginning, I'll probably do some of these, and then I'll stop going over every single line of code because it may be somewhat distracting. All right, so longitudinal data, all right, data that has temporal dynamics, right? There is event ordering that anchors your data into space-time somehow, is what statisticians generally speaking refer to as longitudinal. Now, for those of you that are not interested necessarily with working with some of these test data sets, No problem, because these are large data sets, right? They could be hundreds of megabytes, right? So here I'm kind of showing you how we've actually provided a function that allows you to simulate. In our case, we're very much interested in how the brain operates. How does the brain react to external stimuli like visual, audio, tactile, all kinds of stimuli? How does the brain react? So this kind of allows me to construct a simulated time course of a functional magnetic resonance imaging with certain number of temporal times. Now, most of you know these are about 2 to 3 seconds apart. In reality, when you're inside an MRI scanner, these are going to be 5 repeated runs and 20 subjects, right? So what comes out of this function will be a simulated fMRI data set. And then here is another function that kind of does the plotting, okay? You want to see that data once it's simulated, and we're not going to go through, obviously, all the details, but this is the assignment operator in R, which is essentially equal sign on steroids a little bit, okay? Because the equal sign is a tricky business, right? If you have objects, what does it mean to be objects equal? Are they congruent? You know, so this congruency in R is by the piping operator, as you can see. And now this fMRI data includes 2 conditions. They're on state at which the stimulus is applied while the subject is scanned, and an off state when the subject is scanned at rest. Okay, so this is not an uncommon formalism, and you can obviously have multiple different conditions and so forth. But this is just a demonstration. These are converted to arrays of certain dimensions, and then you go through something very important. Okay, the plotly. If you haven't seen Plotly, Plotly is one of these beautiful modern JavaScript visualization platforms that allows you to essentially gain capability of drawing dynamic SVGs, scale vector graphics objects. Now, most of us are very comfortable with static images, but imagine if our images, our results, our papers have graphs or plots that the user can dive in and interrogate and get additional information that's behind the SVG graphical objects. That's what Plotly does. It's a very elegant thing. It kind of does the usual, right? So you say what the data is, you say what's on the axes, what kind of coloring you want, you know, type, opacity, you know, you kind of set it up, and then you add additional traces, and then you lay it out and return it, right? So here is where I'm actually calling my simulate fMRI function. Now I've got the object created. I've got the data object created. And now I'm calling my plotting function, and then we're going to do a little bit more visualization. So I'm going to hide this because it takes quite a bit of space here, and go directly now to this. Extend a little bit. So if you don't mind, occasionally I'm going to be zooming in and out so that I can see this one doesn't fit. Okay, move this. All right. So what's happening here, to be fully transparent, is I need to scroll down a little bit just for a moment. Okay, this is not here, but so what's happening here is we've just selected one spatial location. So remember, fMRI is spatial temporal data, 4-dimensional. If I fix the 3 spatial dimensions, I have a localization in 3-dimensional space, okay? And then we're going to take the time courses and visualize these time courses for the fMRI signal. Now, what you're seeing here, remember how we simulated on and off 80 time courses, 80 time points, that is. And now, in reality, they're interspliced, okay? So in other words, the 80 and 80, they're not, the first are rest and the next 80 are stimulus conditions. They're interspliced, so, and randomly for that matter, so that you can actually exploit the transitions from an on stimulus state to an off resting state. So this is what, on the background, you can see the original data. This is it, the original data, and then you have a little bit of a smoothed version of that time course. And the reason why there is 160 time points is I have 80 and 80 kind of interspliced, right? Okay, so everybody. And by the way, this is what I meant. Here is your plot. I can take an image out of it. I can obviously zoom in on an area. You know, I can read data off. I can hide some of these guys, right? I can do a lot of manipulations of these graphs interactively. These are not static images, right? So that's where the power, and you're going to see for one-dimensional graphs, you know, this doesn't make a whole lot of difference, but you'll see pretty soon when we start doing this in 3D scenes, how this is going to make a big difference. Another very brief pause here to see if anybody has any questions or comments before we now go into the notion of how do we transform these repeated measurements. Remember, I had 5 runs and 20 patients. These 5 runs and 20 participants are considered repeated measurements of the same phenomenon, of the same process, which we now want to stitch together these time courses, like the ones you see over here, into a surface. So I want to take a pause here just to make sure everybody knows where to find the materials, if there's any questions about R, about the framework, anything else.
I have a question. So why
Yeah, go ahead,
why
Vivek.
did we mix the 80 points which were at rest and then the 80 points which were the on and off? Why did we mix them? That's one question. And the other one was you were talking about time. So here it looks like we collect data and we as humans annotate what t is equal to 0 is. But in a physical system, if you're observing it, like how do you even know where the time origin is? And how do you even really define time there? So those are my 2 questions.
Yeah, so I'll start with the second question, Vivek. So how do you know what time really is however you define the event ordering. The only reason why we use time, and you know very well the dichotomy between, you know, the problem of time and why is time different from space. The only difference between space and time in space-time, in space-time, is that time is the event ordering which only covers the positive reals. And that's precisely why the complex time covers the entire plane to make the temporal dimension more like a space dimension. So in space-time, in the space-time 5-dimensional space, there is no difference between the spatial and temporal dimensions. So, but where you start time? Well, so this is up to you. You have an event at some point, and then you radiate from this event with certain speed, with certain frequency of sampling and all that. This is what you control. But the notion of time is that it needs to be covering positive incremental events, and the way you track them is up to you. For us, it doesn't really matter if the time is recorded in thousands of years, in nanoseconds. It doesn't really matter as long as the data is observed sequentially, and this is the beauty, not necessarily on a uniform sampling scheme. You can have an observation here, you skip 3 years, the observations start on a monthly basis. So that's irrelevant as long as the order of the event is clear, because without ordering of the event, you just don't have a good spatial temporal description of the phenomenon you're monitoring. Now, your second question, Vivek, was regarding why do we need to have 80 and 80, and why do I have to intersplice them? Because if you don't, suppose in the extreme, right, you put the 80 rest conditions first, and you put the 80 stimulus conditions next, okay? And you are not going to be able to see, you only have one chance in the gap from 80 to 81, in the gap to see explicitly what is the effect of the triggering mechanism, which in this case is it's a finger opposition trigger. The subject is asked to do finger opposition. So Whereas if you intersplice them randomly, you avoid the effect of maybe I spent 2 rest conditions and then 1 stimulus and then 3 stimuli after that and 1 rest. Your inference is deeply, deeply affected by the study design is what it's called. It's the event relatedness of how the different conditions are introduced, in this case, to the participant. Is this making sense?
Yeah, so I guess it means data augmentation at some level, or maybe.
You can. Yeah, there is a connection, definitely. There is a connection to data augmentation, and I'm going to come back to this point a little bit later, because you see, once you have the space kime, the complex time representation of the signal, Vivek, it's a manifold. I can sample it at any resolution. So you see, I can literally synthetically generate data of infinite order once I have the space kime manifold representation of the process. So we absolutely right. There is a deep connection there with what in machine learning is called data augmentation.
Yeah, thank you.
All right. Anybody else before we press on here? Okay. So now, how do we now, and this is a critical point, right? How do we go from time courses to one of these time surfaces, which you see down here on the bottom? Oops. Let's see if that would play. Okay, it kind of becomes tight. The GIF runs out of steam. So this, remember, so this time surface is a representation of the entire, let's say, on fMRI repeated sampling of 80, where the time is the radial direction here. Think in polar coordinates. So this surface is parameterized on the flat plane, which we call the kime plane, the complex time plane, in polar coordinates. So the radial displacement is exactly the event ordering, and the phase, the polar angle, is reflective of the random indexing of the specific series. Remember, I have 5 repeated runs for 20 subjects. So I actually have 100 repeats of the same process, the on state, for example, the stimulus of finger opposition. I have 100 repeats. These 100 repeats are radially, angularly representing across the kime surface. All right, so I'm gonna, well, let's keep this for a second, because somebody may want to ask a technical question. So how do we actually go through this transformation from time courses to kime surfaces? That's what I want to just, and you know, there's a lot of technical details on how this can be done. Okay, I will just show it. Okay, so there is a pseudo algorithm again. In the interest of time, I'm not gonna go into the nitty-gritty details, but they're there for you. And maybe at some point we can come back towards the end. I'll make sure, I promise, to stop at 12:45 or 12:40 even, and ask for questions just to make sure we cover all the bases. Now, here is the most important part. The most important part is that you have to, because these are independent realizations, these 100 instances of the off state or the on fMRI state, they're independent instances. So it assumes that you have a controllable experiment that you can reliably reproduce. And now in this specific example, we're reproducing it 100 times because I do 5 runs, 5 repeats for the same individual, and I have 20 individuals. So I have a total of about 100 repeats. So one way to reconstruct the kime surface is to randomly sample from a symmetric distribution, typically with a 0 mean. So here is an example of the Laplace, the double exponential distribution, right? The double exponential decay tails. And as you can see, it's plotted between minus pi and pi. So does everybody see now the angular momentum here, if you wish, the phase from minus pi to pi, covering the spectrum of this radial, of this angular momentum here that you have. Okay, so we are going to be randomly drawing. So I'm going to be randomly drawing from Laplace and assigning to these 100 instances of the repeated fMRI on series, and separately for the repeated fMRI off series, a random phase angle, okay? And then, as you can see here, these things kind of, so here's my time, which I obviously know it's 0 to 80 for each of the two experimental designs. And here is the phi that we are going to be randomly sampling in this case. And again, all the code is over here, how this is done precisely. And mind you, you need to use the outer product here, the outer product, to generate the parametric descriptions of these time series. But here is an example. Again, the technical details are here in full and glory details, because remember, all of these graphs that I'm showing you, they're not static. They're generated on the fly when we compile this notebook using the R package knitter. So here is the on fMRI surface, kime surface, that essentially captures all the 100 instances. So you see, if you bring the mouse over, can everybody see my, so fMRI intensity is 0.037, and this is obviously normalized. The time is, this is the 6th time point, 1, 2, 3, 4, 5, 6. And the phi that was randomly sampled from the phase distribution from this double exponential was equal to 0.31. If I move about here to this peak, phi is negative, and this is the last time point, the 10 point. Now, what's happening here, and I wasn't very specific, but these 80 instances of the fMRI measurement from the scanner actually represent repeats of 8 repeats of 0 to 10 time points. Okay, so we see time equals to 10, and as you move closer to the center, times become 1. At some point, I should be able to get a 1. Okay, right up here. Okay, if you're very clear. So here, by the way, this is the very, very simple. You see, a single line of code generating something that's quite complex, something that you can, a 3-dimensional scene. Okay, and by the way, for those of you that are used to spectrograms and all kinds of other heat maps, this is kind of, if you want to look at it as a flat object, no problem. This is what it looks like, a flat object, right? And I can, again, move the mouse over and kind of understand what's going on. But this is deeper than that. So imagine now the situation where this is the on, this is just the trigger, this is the stimulus condition of the fMRI experiment that we have now. Below it is the corresponding kime surface reconstruction for the off rest condition. Okay, and now you see where I'm heading with this, right? I hope everybody understands. Now I'm interested in finding out which regions in the brain are associated with the finger opposition task. Which regions in the brain are going to be associated with this specific task? And these are going to be the regions that actually show statistically significant differences between these two kime surfaces, the on and off. And by the way, you can easily generate what we call the iceberg plot. So remember, it's very important here to realize that in reality, this is just one single voxel location. This is just one single voxel location. The brain has millions of voxel locations. So spatially, we have fixed one location. We extract the time courses. We reconstruct, well, we take a prior phase distribution. We reconstruct each of the kime surfaces. We modulate them, and now we have the differences. So again, for one location in the brain, I have this difference kime surface model. And what I'm going to be interested in, for those of you again that are familiar with Gaussian random field theory, you're interested in finding out which of these peaks are statistically significant and which of these peaks are random noise. So the Gaussian random field theory says, the excursion sets beyond certain threshold are the ones that you consider significant. So maybe this peak here is significant, maybe that peak is significant, but this other one is not. right? So now, if one of these iceberg plots does not have any statistically significant peaks, this is an indication that the specific spatial localization in the brain that these kime surfaces represent is not engaged in somatosensory processing. Is everybody here with me? On the contrary, if some of these peaks are statistically significant, I can pinpoint precisely at what point in time the on and off trigger, and that specific, not really neuronal cells. We don't have the resolution at neuronal cells. But this specific 1 millimeter by 1 millimeter by 1 millimeter voxel in space seems to be synchronously engaged in the process of finger opposition. Okay, so this is the idea, right? So I hope everybody can understand. So here is a little bit more details about what's happening in reality. So you have a total of 160 time points because my binary study paradigm has only on and off states. If you have 100 states, that will be 100. I have 8 repeats over time, over 10 time points for the fMRI surfaces. So now, then what you want to do is you can look at alternative strategies, right? And again, please forgive me, but we're not going to be able to go over. There is many different strategies for reconstructing the kime surfaces from the observed time courses. So this kind of shows alternative strategies on achieving the same goal, all right? In particular, fitting various models, whether linear or nonlinear, and then your representations of these kime surfaces are going to be slightly different, right? If you change the reconstruction mode, you're going to have slightly different looking kime surfaces, right? So this mapping from the raw time courses into the two-dimensional parametric manifolds is critically important for your inference, as you can imagine. And what I'm saying is that there are different strategies to achieve this, and obviously the inference that you get at the end as to determining which voxels are highly activated and which voxels are not highly activated would be highly dependent on that transformation. All right.
I have a small question, please.
Yeah, go ahead, Vivek.
So I'm trying to understand this. Are you saying like, so analogously, like in quantum mechanics, you have a wave function and then what you measure is just like mod psi square. You don't really there are things which are hidden. In the same way, are you saying like, let's extend that sort of philosophy to time? Say that there's a hidden phase and you actually just see that magnitude and then you're sort of taking this Laplace prior and then like getting the phase and then you have the magnitude and then you do the K1, K2 plot. Is that, I don't.
Okay. Absolutely, Vivek. And this, by the way, is linked to on the website. So I was planning on covering this a little bit later, but since you asked the question, let me just, so I'm going to pause here for a brief moment, just to answer Vivek's question. Because I mentioned in the beginning, okay, quantum mechanics, all these things. Let me just pause here for a second to show you a little bit. And again, this is really deep. So I'm not going to be able to go in too much details, but I just want to show you this section. Everybody's familiar with the quantum tomography, okay? The notion of recovering the enigmatic phases that are not observable. Exactly the same problem, Vivek, appears in space kime analytics. Because remember, when I have these time courses, they're essentially projections. They're in mathematics, they're called foliations. If you look at this kime surface and you think about cross-sectioning it with a vertical plane, the cross-section of this is going to be a time course. Well, this time course is one of your observed phenomena. But if I cross-section it differently, does everybody see how I'm going to be getting different time courses? Right? So the foliation of the kime surface is what is actually observable real phenomena. We are trying to do what in quantum mechanics is referred to as quantum tomography, we can do this in what we call kime phase tomography, okay? And again, all the details are over here. I'll just very briefly, because you asked this question, it's an important question to answer, is how does that actually happen in practice, okay? So you actually formulate different bases, just like what you're doing in quantum mechanics, right? You cannot get phase estimations from operators that are commutative. You're not going to get any additional information. And that non-commutativity, in our case, requires different base representations. And measuring these different base representations gives you different cues. It probes the phase differentially. And when we stitch these things together, you begin to gain an understanding of what is the underlying phase distribution. Because remember, up here, I did a huge, this was a huge assumption. Over here, remember, I said, well, let's go ahead and assume the underlying phase distribution is double exponential Laplace. But what if it's not? How do I know that this is the right distribution? Well, for this, you actually have to do quite a bit of lifting here to get to the point where you can not really guesstimate, but quite rigorously estimate using reproducing kernel Hilbert spaces in it, reproducing and different bases. And again, we kind of talk about, the wavelet basis, the harmonic Fourier basis, and then how do we actually obtain an estimate for the phase distribution in each base separately, and then how do we aggregate them together? Because each of them, it's almost like looking at the spectrum, right? If you have a signal and you only look at a small frequency spectrum, you only understand so much about a signal. But if you have different spectral locations, now you can, all of a sudden that kind of overlap, you can almost perfectly reconstruct the signal, okay? So this kind of shows you an example of how the phase distribution can be estimated from having different bases, and in this case, it's just two bases, and using non-commutative operators, okay? So the physics is very, very deep, and you're absolutely right. It's exact translation of quantum physics into the analytics world, where now our observations are actually represented in different, we call them kime test function bases. Okay, so and again, for those of you that want to understand more about the underlying phenomena, I would recommend, or maybe I'll leave this at the end, Vivek, because we're not going to. It's just we can spend a day literally going over that. So if it's okay, Vivek, I press on to finish this, and then at the end maybe we come back a little bit. All right. So any other questions or comments before we go a little bit deeper? So different reconstructions give you different kime surface models for your process. And obviously, these correspond to different inferences at the end. All right. So here is an example. Now, if somebody is not satisfied with a parametric kime surface modeling, we also have an analytic, fully mathematically holomorphic function representation. Okay, and this is how this is done. And we have a paper on this. I don't want to bog you with the details. But here is, in a nutshell, what's happening here. In a nutshell, the Laplace transform takes a time index function, f of t, and transforms it into a complex valued function over the complex domain. So the Laplace transform is literally an analytical function that maps time series data into kime surfaces. And here is an example of something that we can do exactly by hand, looking at simple functions, okay, sine and cosines. And by the way, just like I said, the Laplace transform is a complex valued function over the complex domain Z. Okay, so here's my, does everybody see the real and the imaginary part of Z? The vertical, because it's a complex function, I can only plot in a three-dimensional scene real values, as you can imagine. So this is just the magnitude, okay, in this specific case, okay, the magnitude of the complex kime surface. But that's what they look like. So if you're not satisfied with doing this numerically, the way I suggested earlier with many, many different alternative time series to kime surface parametric transformations, you can do this analytically through the Laplace transform, okay? And here is one kind of a little bit more nuanced example. Yeah, so here is your, so suppose my function is literally cosine with a little bit of noise. Think about adding a little bit of noise to this. Oscillatory, perfectly well-behaved signal. The Laplace transform can be completely and analytically computed. As you can see here, that's what it is. And obviously, once you can compute it, you can plot it, okay? That's what it looks like. Now, imagine if I have sine and cosine, two completely different, so on signal corresponds to cosine, off signal corresponds to sine. I have two of these kime surfaces. I can very easily do, I mean, you know, at the easiest point, okay? At the easiest point, you can do manifold distances, okay? And quantize or statistically represent the distribution of these distances to obtain inference, right? And I mean inference in a very, very broad sense. Classification, regression, prediction, for whatever you want to do. But you can imagine how much richer AI models that are based on these surfaces are going to be compared to AI models that are based on signals that only go up and down, up and down, up and down, time series. These surfaces have complex structure, curvature, fractal dimension. You know, in the analytic case, you can compute derivatives. So you see the point here. These kime surfaces are mathematically very rich objects that you can build advanced AI systems to do your bidding, basically. All right, so that's interesting. Okay, and here is one simple kind of model. You know, it takes in the one-dimensional on and off sequence means averaged over the, remember, we have a whole bunch of repeated samples. So these are the corresponding averages. So now I can compute their corresponding Laplace transforms. And here is the magical, here on the bottom is the magical difference that this is almost like the signature, right? The manifold signature that discriminates the on and off fMRI data that we looked at, right? So everybody see? That's what it looks like in the Laplace world. I showed you earlier two different reconstructions. Okay, so we can use integral transforms as well. You know, these are kind of standardized. Hilbert transform, you can use Fourier transforms and all kinds of other transforms to obtain reconstructions that are somewhat different, right? Okay, but again, the same idea, iceberg plot, which represents the difference, and the original reconstructions on the left-hand side. All right, now, all right, so here are more examples. And again, you see the different reconstructions here, they correspond to different slightly modified strategies. Again, we're not going to go over all the details, but if anybody's interested, we can take this offline and talk about how are all these different and why are they different and why are some of these prickly and some are smoother, right? Because, you know, noise is present always in observations. We all know that, you know, whether the noise is machine-driven, factor-driven, or intrinsic, like quantum fluctuations, that's a very different discussion point. So here is the thing that I should have probably showed you in the very beginning. Here is the local. Does everybody see the spatial? I know this doesn't look. Let me see if I can zoom out a little bit. Okay. So this is what's called axial cross-section of the fMRI. This is the real fMRI data now. This is not the simulation I showed you before. This is real fMRI data. We've picked one. You see the crosshairs in all these axial, sagittal, and coronal planes. Remember the brain viewer that I showed you in the beginning when I did the cross-sectioning? It showed me cross-sections in three-dimensional scene. I'm seeing the projections of these cross-sections, and these are kind of specified over here by the crosshairs in each of the three planes. Now, again, SVG objects, I can actually zoom in, read the intensity, and kind of manage this. This is, of course, the blue is the actual data. This is real data, and now you have exactly the same paradigm, which we simulated earlier, but now this is real data talking. No simulation here. And by the way, again, if you want to see how the data is loaded, have a look at these hidden code segments. All right, so now the first one is essentially without a spatial temporal mask restrictions. See, the spatial temporal mask, see the extracerebral activation here? There is no extracerebral activation. It's just noise from the scanner. And quite frankly, this disturbance due to non-homogeneous magnetic field. Remember, these MRI scanners operate at, 1.5 to 7 Tesla, right? These are huge magnetic fields, very easily disruptible by, so this kind of noise, sometimes you may want to kind of triage, okay? So with and without masking restrictions. And then you extract, see what we did now here is we took the data from 0 to 140 or 130, yeah. We took the data from 0 to 130 as learning, training data, and we predicted forward the expected signal without necessarily knowing even what paradigm. Was it a rest condition or a trigger stimulus condition? You don't have this information. The red curve is the actual forecast. The bands, as you can see here, the blue and orange bands represent high and low confidence level. I suspect everybody understands what confidence bands are here, right? Obviously, the higher the confidence, the broader the bands, the lower the confidence, the tighter the bands, right? And then the real signal is superimposed, and you can see, with the exception of over here and these three instances, we're mostly capturing in the confidence limit, not in the instance of the prediction. And obviously, as you move away, the accuracy of the instance prediction is going to be going down. So this is just one example of how these things work. Again, remember, this was in a single location in the brain. This is just a one spatial voxel. All right. So then what we can do is now we can obviously do this for the entire brain, okay? And you specify a threshold level, okay? And when you do this for the entire brain, you get an image. So for those of you that are not very familiar, the eyes of the brain are going to be right up here. Here is the left eye, and the right eye is going to be over here, okay? And as I move around, you can see I can see these cross sections that we saw above earlier, right? Now, I may want to only show the very, very highly significant p-values. No problem. This SVG allows me to hide the non-significant voxels. And look what I end up with. Once you triage the noise, exactly the somatosensory brain cortex, which is on the left and right hemisphere, right up here, between the frontal lobe and the occipital and the parietal lobe, is what's called the somatosensory cortex. So here are the voxels. Again, the eyes are over here on the front. Here is the cerebellum in the back. And you can see the bilateral activation that we are detecting right where we expected to see in this specific finger opposition task. So in other words, I guess shortly what I'm saying is that this method kind of works, okay? And again, if you see that there's a lot of random noise, okay? Non-significant. This is the range between 1 in 100 to 5 in 100, right? So this is kind of a lot of sparse, because remember, there is literally, I kid you not, millions of statistical tests that are carried here. So the notion of correction for multiple statistical testing is pivotal here. That's exactly why we're kind of visualizing mostly, you know, the highly significant areas, because that's where the action is. Now, in this specific way, in the next specific example, we actually account for what's called the hemodynamic response function. See, the brain is a very interesting beast, okay? You stimulate it, and the activation shows up in the fMRI data delayed. And the delay is actually a distribution, effectively. Engineers and statisticians call it hemodynamic response function. So it doesn't, the detectable signal doesn't pick up for a few seconds, then it shoots, then it undershoots, and then it settles back. So we can imagine as we tweak from on to off states, sometimes the previous on state is going to bleed into the next sequential state. It could be on, it could be off, you don't know. But that hemodynamic response function is an interesting one. And then the previous state is going to be bleeding into the current state. So accounting for hemodynamic response function is kind of important. Okay, and these are just cross sections, just to show you the contour of the brain a little bit with exactly what. So the front cortex is over here. Here is the brainstem. Here is the occipital visual area, and the cerebellum is not shown. It's kind of below here. But here is where the somatosensory cortex is. The frontal and parietal border. It's actually two gyri, two crests where the action happens. Okay, in the coronal view, like this was sagittal preview. This is a coronal view. You get these maps, and then at the axial level, you got some of these things, and you can kind of modulate various visualizations and so forth. Now, as you can imagine, you know, the statistical inference doesn't stop with you generating these massive, this is not quite all voxels, but a large number of voxels are shown here, right? How do you actually know what's significant and what's not, right? And for this, we actually have multiple, we have a phase 1, phase 2, and phase 3 inferential procedures. Again, the details are important, but not critical at this level, right? There are functions in the TCAU package to do these phase 1, phase 2, and phase 3. So the basic idea is that you see, phase 1 asks the following question. What bigger regions in the brain, think about right frontal lobe, left frontal lobe, superior temporal lobe, ventral V1 area in the visual cortex, cerebellum, hippocampus, in the middle of the brain. You're basically asking the question, which regions are statistically active and which regions are not? The regions that are not showing global regional activation are discarded before you go to phase 2. In phase 2, you've said, okay, well, maybe in the singular gyrus in the frontal lobe, or in the superior frontal associative cortices, maybe these are showing global regional activity. So then you're going to go voxel by voxel, walking through every single location in this region and doing, I know most of you are familiar with what's called tensor on tensor regression. The reason is that your data and your covariates in your data are not really scalars anymore. Remember, these kime surfaces, they're tensors. They're multidimensional arrays. So you have to kind of go one level higher. You have to do tensor on tensor regression. And then these are going to tell you, well, which voxels specifically in the activated regions are active and which are kind of, mostly silent. In phase 3, you're going to do the FDR correction, false discovery rate correction, for the millions of statistical tests that this procedure involves. So through these 3 steps, you're kind of zeroing down exactly on the most highly significant spatial locations where action is associated or correlated with the on and off and on and maybe different phases, if different phases are shown to the participant, if different stimuli are applied, whatever. You're looking for correlations with brain activation. So here is the original brain, okay? And again, there's a lot of regions. I can actually suspend some of these, right? If you toggle them off, you see how now I open a gap here in the brain, right? So this is how you do the regional, it's called ROI, region of interest activation in phase 1. In this specific case, these are the regions that were statistically important. So here is your, on both hand sides, you see the red region over here, post-central gyrus, and then right up here, left precentral gyrus, and left post-central, right behind it, okay? And there were also a little bit of the frontal area that was activated. So we're, in phase 2, we're only gonna focus on these regions, right? So once you do that, you get these are the tensor regression inference. And now, model-based inference, you may not be a huge fan. It's probably fine. There is other inferences, but you can see how easy it is to swap a method. And then finally, you actually do the phase 3 model, where now you're actually only left with the statistically significant regions. Okay, so these are the p-values at the phase 2, and this is phase 3 stage. All right, and then you can obviously do some of these things. Here is a little bit about kime surface tensor on tensor regression. Again, if people are interested in how exactly this thing happens. So, you know, I guess the simple way to explain this is you take a linear model in a matrix format, and you call it a tensor model, right? So here is my output tensor. Here is my design matrix, is what we call it in statistics. This is the input covariance predictors that are going to be used to forecast the outcome. And here is my effect sizes in the multivariate regression model. These are going to be the tensor now effects. And you're going to be using, obviously, a proper inner product here, okay, because you're having tensors now. And you're going to have the residual tensor, just like the residuals in classical regression, okay? Okay, so that's what's happening, and you can kind of do some of these things. Now, if you're more excited about, you know, linear models, you know, this is almost 19th, 20th century technology. Linear models, we all know, we love them, but they've got huge assumptions. Most of the time, I would say that 90% of the time when linear models are used, the assumptions are invalid. Parametric assumptions, you know, of all kinds, and that when they're slightly violated, it doesn't really affect the inference. The problem is that we don't have the very often times sufficient information to argue whether or not you know, homoscedasticity is a reasonable or irrational assumption. So how about then we use a topological kime surface analysis? So a topological, obviously this refers to TDA, topological data analysis, which you all know has to do with essentially reconstructing you think of the data as being in a very, very high dimensional point cloud. And you're asking yourself, yeah, most of the time when data is embedded in a high dimensional space, the core of the data is intrinsically lower dimensional. Because if it's not, it's total, utter chaos and random noise. But if it has a pattern, if it has structure, this structure manifests as being a lower dimensional manifold. And topological data analysis in the classical sense and topological kime surface analysis in the more modern sense address that notion of modeling the data in this high dimensional space using different structures. So again, here are some of the details. I won't bother you too much other than saying that, you know, classical methods are used to assess you know, manifold distances and all that business. And we've actually done examples to illustrate kime surface analysis with some of our data. So here is, for example, a surface plot of the difference, which is in the middle, and then its corresponding its corresponding bands, that kind of capture the variability. Yeah, this is a little bit of a better plot that kind of shows you the model and then how much dispersion around this model you can get. And here is in essence what it does, right? This is what's under the hood, right? Under the hood is that you want to use simplicial decomposition. So let me put it bluntly. In topology, you have basic building blocks, like points are called 0 cells, lines are called 1 cells, triangles are called 2 cells, tetrahedra are called 4 cells, and so forth, right? So these are the basic building blocks that every manifold can be decomposed into. No matter what the dimension, no matter how complex the manifold is, right? You can decompose it in its building blocks. And the question with topological data analysis in general is how do we fit a manifold of certain dimension to a high dimensional data? And here is the corresponding kime surface representation with the corresponding derivations, as you can see here, from the topology, the derivations of the different regions. So I hope everybody sees what's happening here. We are essentially obtaining unsupervised topological kime surface classification. And the classifications of these points are different colors. Okay, so you can do that as well. You can obviously do non-parametric statistical inference on kime surfaces, as you can imagine, right? Because earlier we said, well, we're going to do classical, parametric t-tests, ANOVAs, linear models, whatever. But you can obviously do non-parametric testing as well. And here is for our kime surfaces the corresponding what TDA calls the barcodes. So these barcodes are the representations of the topological decomposition across different scales. So think of it as multi-resolution, multi-spectral decomposition of the manifold that's fit. And then using these things, you can see that you can obtain real quantitative analytics. And again, I won't bother you too much with the details here, but these things. So here's a permutation test. Everybody knows the permutation test. A very valuable, highly useful non-parametric test. Slightly less sensitive to parametric tests, however, more useful because of its lack of these heavy-duty prior assumptions that you have. So, all right. So I want to pause here now for a second with questions and maybe even return to the kime phase tomography that I mentioned earlier. So this is essentially the end of the formal presentation of this tutorial. I just want to very briefly recap. That's where you start. This is what we're trying to reconstruct, these kime surfaces from multiple repeated samples of the same processes. Think of these as being IID time series, independent and identically distributed time series, that you want to stitch together the repeated measurements into these kime surfaces. Then we're going to use electronic markdown notebooks to encode everything from the start to finish, okay, in these electronic markdown notebooks. That's how they get rendered. And then you can use R Studio or any other graphical integrated development environment, IDE, to build, test, run, and compile these electronic notebooks into tutorials like this. All right, so that's a good time for me to pause here for a second and see if people have if people have questions or comments. Now is the time. We have about slightly less than 10 minutes, but let's say 10 minutes.
I have just like 2 quick questions.
Yeah, go ahead.
So just like we can go from complex numbers to quaternions, can we go from kime surfaces to QIME, like QIME, like quaternion time representations giving? That's one. And the second question is, can you, let's say you want to do time series regression, can you get a kime surface and then do like a complex valued neural representation, and then you'll have to, like, I don't know, use Vertinger calculus because your loss function is non-analytic, but can you sort of do regression in a complex space with these? So these are my 2 questions.
Yeah. So I'll address the second question first, Vivek. The second question, remember the example that I showed with tensor regression? That's the first example of how you can do exactly what you're asking, right? The kime surface modeling with what I tend to call model-based, not really classical, but model-based statistical method. The more powerful aspect of the second question is what you refer to as now networks. And I will tell you, again, the notion that these very, very mathematically enriched objects, these kime surfaces, they can be used to obviously develop and train advanced either large language models or, generally speaking, what I call games generative AI models. It doesn't really matter what the architecture behind that structure is, and maybe even the architecture could be a kime surface itself, you know. But yes, we haven't done that, you know, because we, you know, there's so many hours in the day, I guess. So the answer to the second question is yes, you can, and you can do this for both model-based and model-free inference. Regarding the first question, which was about...
So I was saying you can go from complex numbers to quaternions, like just...
Yes, the quaternions, yes.
So does time have a vector nature, and can you go to QIME surfaces?
Absolutely, right. So there is nothing special with the complex plane except that it's got two properties that no other field has. The first field, Vivek, is that the complex plane, the kime plane, is the smallest prime field that naturally extends the positive reals. There is no other smaller or complete prime field between the positive real multiplicative group and the complex plane. There is nothing in between. Second of all, yes, you can go to quaternions. And in fact, we've actually, because you can have infinitely many phase dimensions. That's true. But if you go to higher dimensions, 2, 3, 4, obviously 3 is a bad case because the 3-dimensional, it's not even a field. So you got to go to the 4-dimensional quaternions. You're absolutely right. And you can do that, and you're going to get, maybe the results are going to be better, Vivek. We haven't done this. But you got to go to quaternions, and then higher order are going to be infrequent because they have to have the mathematical rigor of being a complete field, which not every manifold of any dimension does, even if it's a flat manifold. See? So remember, the kime plane is kind of unique in a way, right? Is the smallest possible complete prime field over the reals. There is nothing better than that. Now, you might be able to get to a higher dimension and get even better results, but that's a good ground starting point, I suppose, if that makes sense. Other questions, comments, everyone? You can put them in the chat. As Julie said, you don't have to speak. Or you can send either Julie or I an email later, and we can connect offline. So again, my hope is that because all of this is true open science, you will be able to offline, you know, traverse some of these things. I'm sure there will be mistakes here and there. I know every time we look at these things, there is always typos. But send us any comments, corrections, revisions, anything that comes to mind is always welcome. I'm looking at the chat. Okay. Yeah, so